This video is meant to go over question 5 in the 2018 AP Chem FRQ. This is a short response question. In this question, we have the equilibrium reaction between hydrofluoric acid and water so that it dissociates into the two ions, and that weak acid dissociation is represented by the equation above. In a 0.035 molar solution, the percent ionization is 13%. There are 3 parts to this question. The first part is we're doing an analysis of 2 particulate drawings, and they want to know why figure 1 is more accurate. In part B, we're going to use the percent ionization, which is 13%, to calculate the Ka value for hydrofluoric acid. And the last part, they want to know what would happen if 50 ml of distilled water is added to 50 ml of the 0.035 molar hydrofluoric acid. So we're going to break this up into 3 different parts. In part A, they want us to compare 2 figures and explain why figure 1 is a better representation of the ionization than figure 2. So let's take a look first at figure 2 and see what's going on there. I've got this molecule right here is my H3O, my hydronium ion. So I have 1, 2, 3, 4, 5, 6, 7, 8 of those. Probably a good idea. If they give you particulate drawings, go ahead and count how many you have of each one, and I circle them just so I know what I have. I've got this one, and so let me count those. I've got 1, 2, 3, 4, 5, 6, 7, 8 of my fluorine ions, and I have 0 of my HF, which means that, and that's my reactant. So this shows that I have gone to completion. I don't have any of my reactant, which is HF, left. Now in figure 1, all I have is 1 hydronium ion. I've got 1 fluorine ion, and I've got 1, 2, 3, 4, 5, 6, 7. So I've got 7 of my HF. So 1 out of 8 of my HF disassociated. And if you do the math for that, 1 divided by 8 gives you about 13%. So that would be a better representation of the disassociation than figure 2. So part B of this problem, we're asked to use the percent ionization to calculate the Ka value. And although this is not included on the 2020 exam, equilibrium is, so using rice tables is probably good practice for the equilibrium part of the exam. From the molar relationship here, we can assume that the concentration of my hydronium ion is going to be equal to the concentration of my conjugate base. And I also know that the ionization is 13%. So 13 divided by 100 gives me 0.13. If I multiply that by my initial concentration, which is 0.0350, that gives me a concentration of 0.00450, which is the concentration of both of those ions when it disassociates. So now I'm going to set up my rice table. Okay. My reaction, I'm going to disclude, I'm just going to take out the water from this reaction because we don't include it in our rice tables. Initially, I know that I have a concentration of 0.0350 of my weak acid. I don't have anything disassociated yet. My change is I know I'm going to go down by 13%, and I figured that out right here. So I'm going to go down by 0.00450, which means that both of these are going to go up because of the molar relationship is 1 to 1 to 1. They're going to both go up by the same amount. Oops. Okay, so my equilibrium concentrations for all substances are going to be 0.0304, and then for both of my products 0.00450. Okay, so that's my rice table. Now I need to set up my Ka expression. My Ka expression is products over reactants. So I've got my hydronium ion multiplied by my fluoride ion over my weak acid. Okay, which means I've got 0.00450. This is all, I'm taking my equilibrium concentrations because this is my equilibrium constant. Since they're both the same, I'm going to square that. And 0.0304. So my Ka value should equal 6.81 times 10 to the negative 4. So in this last part of the problem, we are adding 50 mLs of distilled water. So we're diluting down our original concentration. And they want to know what's going to happen to the percent ionization of our weak acid. Will it increase, decrease, or remain the same? They're asking us to justify with an explanation or calculation. I'm going to do this with a calculation. We are going to compare our reaction quotient, which is Q, to our equilibrium quotient or equilibrium constant, which is K. So we need to know what our equilibrium constant expression is. So I'm going to rewrite that. It is our products in solution. We're not going to include any of our pure substances in the expression over our reactants. Okay, now let's talk about our Q. So what's happening in our Q? If we're adding 50 mLs to our original, so what we're doing is we are doubling the volume of our solution without changing the molarity at all, which means that our concentration or our molarity is going down by a factor of 2. Okay, so in other words, we're going to have half of our molarity. So if we look at our Q expression, we're going to have, remember these brackets all mean molarity or concentration. We're going to have half the original concentration of our fluoride ion. We're going to have half the concentration of our hydronium ion because everything's going down by a half. And we're going to have half the concentration of our weak acid. If I break this up, I can simplify this by getting rid of that. So my Q is going to be equal to 1/2, and the rest of this is my K expression. So it's equal to 1/2 my K expression, which means that my Q is going to be less than my K. And if I look at, so if this is my K, if my Q is greater than K, I need to go in this direction to get back to K. If my Q is less than K, I need to go back in that direction to get to K, which is my equilibrium. Which means if I'm going in this direction, I am going to produce more product. And if I produce my product, my percent ionization is going to increase. So hopefully this gives you some better clarity on this question. This gets us to the end of question 5.